Hey there, welcome. Today we're going to dive into the world of real analysis, a subject that's fundamental to all of higher mathematics. Our goal isn't just to learn some definitions, but to develop something far more valuable: mathematical maturity. Think of it this way: mathematical maturity is like learning to think like a mathematician. It's the ability to break down a complex statement, identify the tools you need, and construct a logical, rigorous proof. That's what we'll be building today. We're going to focus on 3 key proof techniques that are essential building blocks. By the end of this video, you will be able to, first, construct a formal epsilon-delta proof to establish a limit. Second, prove that a sequence converges using the direct method of definition. And third, use the principle of mathematical induction to prove properties of integers and sequences. Let's get started. First up, the epsilon-delta proof. This is a cornerstone of analysis. It might look intimidating at first, but it's built on a very intuitive idea. When we say that the limit of f of x as x approaches c is L, we mean that we can make the function's values, f of x, as close as we want to L. The epsilon-delta definition makes this statement precise. Here's how it goes. For any positive number epsilon, no matter how small, there exists a positive number delta such that if the distance between x and c is less than delta, and not 0, then the distance between f of x and L is less than epsilon. Let's break this down. The epsilon is a challenge. You pick a target distance around L. Your job is to find a delta, a zone around C, such that any x you pick from that zone gets mapped into your target epsilon zone. Think of delta as your answer to the epsilon challenge. You're guaranteed to always be able to find such a delta. Let's prove our first limit. The limit of 3x minus 2 as x approaches 2 is 4. This is a linear function, so the limit is just the function value. But let's prove it rigorously. Our goal is to show that for any epsilon greater than 0, we can find a delta such that whenever the absolute value of x minus 2 is less than delta, the absolute value of 3x minus 2 minus 4 is less than epsilon. The key is to work backward. We start with the conclusion we want to reach and manipulate it to find a relationship with the condition we're given. We start with our target, the absolute value of f of x minus L, which is 3x minus 2 minus 4. We simplify the expression inside the absolute value. 3x minus 6. We can factor out a 3 to get 3 times the absolute value of x minus 2. Aha! Look what we have. The absolute value of x minus 2, which is part of our given condition. We now have a direct link between the two parts of the definition. The absolute value of 3 times the absolute value of x minus 2 is less than epsilon. Dividing both sides by 3 gives us the absolute value of x minus 2 is less than epsilon over 3. This gives us our delta. If we choose delta to be epsilon over 3, then whenever the absolute value of x minus 2 is less than this delta, our original expression, the absolute value of 3x minus 2 minus 4, will be less than epsilon. Now, let's write out the formal proof. Let epsilon be any positive number. Choose delta to be epsilon over 3. Assume the absolute value of x minus 2 is between 0 and delta. This implies the absolute value of x minus 2 is less than epsilon over 3. Multiplying both sides by 3, we get the absolute value of 3x minus 6 is less than epsilon. Finally, we rewrite this as the absolute value of 3x minus 2 minus 4 is less than epsilon. This completes the proof. Our next example involves a quadratic function. Let's prove that the limit of x squared minus 10x plus 29 as x approaches 5 is 4. Again, we start by working backwards from our target. The absolute value of the function minus the limit must be less than epsilon. We simplify the expression, x squared minus 10x plus 25. Notice this is a perfect square trinomial, which is the absolute value of x minus 5 squared. This one was very convenient. We've immediately isolated the absolute value of x minus c term. Taking the square root of both sides, we find that the absolute value of x minus 5 must be less than the square root of epsilon. This means we can choose delta to be the square root of epsilon. Let's formalize the proof. Let epsilon be a positive number. Choose delta to be the square root of epsilon. If the absolute value of x minus 5 is less than delta, then the absolute value of x minus 5 is less than the square root of epsilon. Squaring both sides, the absolute value of x minus 5 squared is less than epsilon. We rewrite the left side as the absolute value of x squared minus 10x plus 25, which is less than epsilon. And this is exactly what we wanted to show, completing the proof. Our third epsilon-delta proof is a bit more challenging and introduces a common technique for handling nonlinear functions. Let's prove the limit of x squared as x approaches 3 is 9. Following our process, we start with the absolute value of x squared minus 9 is less than epsilon. We can factor this into the absolute value of x minus 3 times x plus 3 is less than epsilon. This gives us the absolute value of x minus 3 is less than epsilon divided by the absolute value of x plus 3. Here's our problem. Delta depends on x, but delta must be a constant. To fix this, we need to bound the absolute value of x plus 3. We can do this by limiting our search for a delta. Let's start by assuming delta is less than or equal to 1. This means the absolute value of x minus 3 is less than 1. This bounds x between 2 and 4. Therefore, the absolute value of x plus 3 is between 5 and 7. Since we're dividing by x 3c, we want to find the largest possible value, which is 7. So we can replace the denominator x 3 with the constant 7. This gives us the absolute value of x minus 3 is less than epsilon over 7. So a candidate for delta is epsilon over 7. Our actual delta must be the smaller of our initial assumption, 1, and this new value, epsilon over 7. We must always take the minimum. The delta must satisfy both the bound we created and the condition for the limit. Let's formalize. Let epsilon be positive. Choose delta to be the minimum of 1 and epsilon over 7. If the absolute value of x minus 3 is less than delta, it means x3. 1 and x3. 7 from x3 sa 1 we showed x3 7. So x3 success. EP7 7. Sa c. Thus by x squared minus 9 is less than epsilon on proving the limit. Okay, let's move on to our second topic, proving the convergence of a sequence. This concept is fundamental to understanding limits of functions, series, and much more. The formal definition for a convergent sequence looks very similar to the epsilon-delta limit definition we just saw. A sequence, a sub-n, is said to converge to a limit L if, for every positive number epsilon, there exists a positive integer n, such that for all integers n greater than n, the absolute value of a sub-n minus L is less than epsilon. Let's unpack this. Epsilon is still our challenge, a target distance from the limit L. This time, our answer is the integer n. N represents a point in the sequence. For any term a sub-n after the nth term, we are guaranteed that a sub-n will be within epsilon distance of L. In other words, eventually, all terms of the sequence will get and stay arbitrarily close to the limit L. For our first example, let's prove that the sequence with the nth term 3n divided by 2n plus 1 converges to 3 halves. The process here is very similar to epsilon-delta proofs. We'll start with the conclusion we want and work backward. We want to find n such that for all n greater than n, the absolute value of 3n over 2n plus 1 minus 3 halves is less than epsilon. We combine the fractions and simplify, which gives us the absolute value of negative 3 over 2 times the quantity 2n plus 1. Since n is a positive integer, 4n plus 2 is positive, so we can remove the absolute value signs. We now need to find n such that 3 over 4n plus 2 is less than epsilon. We just need to solve this inequality for n. This inequality tells us that if n is larger than this value on the right, the condition will be met. This is exactly what we need for n. So we choose n to be the smallest integer that is greater than this expression. We often use the ceiling function for this. Now for the formal proof. Let epsilon be a positive number. Choose n to be the ceiling of 3 over 4 epsilon minus 1 half. Assume n is greater than n. Then n is greater than 3 over 4 epsilon minus 1 half. Working backward from here, multiplying by 4, adding 2, and taking the reciprocal, we get that the absolute value of our expression is less than epsilon. This verifies that our chosen n works, and the sequence converges to 3 halves. In our next sequence convergence example, we'll encounter a common hurdle, which is a quadratic term in the denominator. Let's prove that the sequence with the nth term 3n squared divided by 5n squared plus n converges to 3/5. As always, we set up our target inequality and start simplifying. The absolute value of our nth term minus the limit must be less than epsilon. We find a common denominator and simplify, which gives us the absolute value of negative 10n minus 8 all over 5 times n squared plus 4. Since n is positive, 10n plus 12 and 5n squared plus 4 are both positive, so we can drop the absolute values. We get 10n plus 12 over the denominator is less than epsilon. This inequality is not easy to solve directly for n. This is where a key technique comes in: bounding. We're looking for an upper bound for the expression that's simpler and still gets us to our goal. We can see that 10n plus 12 is less than 10n plus 12n, which is 22n. This is an overestimate, but it's okay because we want the expression to be less than epsilon. In the denominator, 5n squared plus 4 is clearly greater than 5n squared. So, our new, simpler inequality is that 22n over 5 times 5n squared is less than epsilon. This simpler inequality is now easy to solve for n must be greater than 22 over 25 epsilon. So we choose our n to be the ceiling of this value. The formal proof is now straightforward. Choose this n. If n, then n 22 over 25 epsilon. Working backwards, we get that our simplified expression 22 over 25n is less than epsilon. Now we just need to show that our original, more complex expression is less than this simpler one, which we did with our bounding. This proves convergence. Our final sequence example is another classic and important one. Let's prove that the sequence with nth term 1 over n converges to 0. We've all seen the graph of y equals 1 over x getting closer and closer to the x-axis. Now we'll prove it rigorously. Our target is to show that for n large enough, the absolute value of 1 over n minus 0 is less than epsilon. This simplifies to the absolute value of 1 over n is less than epsilon. This one is actually very straightforward. Since n is always a positive integer in our sequence, the absolute value of 1 over n is just 1 over n. So our inequality simplifies to 1 over n is less than epsilon. Solving for n gives us that n must be greater than 1 over epsilon. That's it. Our choice for n is simply the ceiling of 1 over epsilon. This value of n guarantees that every term in the sequence after this point is within epsilon distance of 0. Let's formalize the proof. Let epsilon be a positive number. Choose n to be the ceiling of 1 over epsilon. This means n is an integer and n is greater than or equal to 1 over epsilon. If n is greater than n, then n must be greater than 1 over epsilon. This implies that 1 is less than epsilon times n, so 1 over n is less than epsilon. Since 1 over n is positive, we can write this as the absolute value of 1 over n minus 0 is less than epsilon, and our proof is complete. The sequence 1 over n converges to 0. We've covered limits of functions and limits of sequences. Now let's explore a powerful proof technique that is essential for working with integers: the principle of mathematical induction. Induction is a bit like a chain of dominoes. If you can knock over the first domino, and if setting off any one domino always knocks over the next one, then the entire chain will fall. More formally, to prove a statement P of n for all positive integers n, we follow these two steps. First, we prove the base case. The statement is true for n equals 1. This is knocking over the first domino. Second, we prove the inductive step. We assume the statement is true for some arbitrary integer k. This is called the inductive hypothesis. And then we show that it must also be true for the next integer, k plus 1. This is showing that one domino knocks over the next. Once you've done both of these steps, you can confidently conclude that the statement is true for all positive integers. Let's start with a classic example, proving the formula for the sum of the first n positive integers. First, the base case. Does this formula hold for n equals 1? The left side is just 1. The right side is 1 times 1 plus 1 divided by 2, which is also 1. Since both sides are equal, the base case is true. The first domino falls. Now for the inductive step. We assume the statement is true for an arbitrary integer k. This is our inductive hypothesis. We assume the sum up to k is equal to k times k plus 1 divided by 2. Our goal is to prove the statement is true for k plus 1. We need to show that the sum up to k plus 1 is equal to k plus 1 times k plus 2 divided by 2. We start with the left side of pk plus 1 and look for an opportunity to use our inductive hypothesis. The sum 1 plus 2 up to k plus 1 can be written as the sum up to k plus the term k plus 1. By our inductive hypothesis, we know the sum up to k is k times k plus 1 over 2. We substitute this in. Now we do a little algebra. We find a common denominator and combine the terms. This gives us k squared plus k plus 2k plus 2 all over 2. This simplifies to k squared plus 3k plus 2 over 2. Factoring the numerator gives us k plus 1 times k plus 2 over 2. This is exactly the right side of pk1. We have successfully shown that if pk is true, then pk1 must also be true. Since we've proven the base case and the inductive step, we can conclude that the formula holds for all positive integers n by the principle of mathematical induction. Induction isn't just for formulas. It's great for proving properties about integers, like divisibility. Let's prove that for any non-negative integer n, the expression 3 to the 2n plus 2 to the n plus 2 is divisible by 5. Remember, divisible by 5 means that when you divide the number by 5, the remainder is 0. In other words, the number can be written as 5 times some integer. So we want to prove that 3 to the 2n plus 2 to the n plus 2 equals 5k for some integer k. Base case, for n equals 0. P of 0 is 3 to the power of 0 plus 2 to the power of 2. This is 1 plus 4, which is 5, and 5 is certainly divisible by 5. So the base case is true. Inductive hypothesis. Assume that for some non-negative integer k, 3 to the 2k plus 2 to the k plus 2 is divisible by 5. This means we can write it as 5 times some integer m. Now we must prove the statement for k plus 1. We need to show that 3 to the 2 k1 plus 2 to the k1 plus 2 is also divisible by 5. This one is tricky. The key is to expand pk plus 1 and look for a way to substitute the expression for pk. We expand pk plus 1 as 3 to the 2k times 3 squared plus 2 to the k plus 2 times 2 to the 1. This gives us 9 times 3 to the 2k plus 2 times 2 to the k plus 2. Now, let's rearrange our inductive hypothesis. We know 3 to the 2k equals 5 m minus 2 to the k plus 2. We substitute this into our expanded expression. We're not there yet because 7 isn't divisible by 5. Let's try another approach. Isolate 2 to the k plus 2 from the hypothesis. From the hypothesis, 2 to the k plus 2 equals 5m minus 3 to the 2k. We substitute this instead. This is better. We have a term 10m that's divisible by 5. Now we just need to show that 7 times 3 to the 2k is divisible by 5. Remember the property of modular arithmetic. 7 is congruent to 2 modulo 5, and 3 squared is 9, which is congruent to 4, or negative 1 modulo 5. So 7 times 3 to the 2k is congruent to 2 times negative 1 to the power of k. If k is even, this is 2. If k is odd, this is negative 2, or 3 modulo 5. So the expression is not always divisible by 5. There seems to be a mistake in the problem statement. This is a great example of where trying to prove a false statement can teach you a lot. Let's look closely at the problem statement. Ah, I see. My example has a typo. The correct statement is 3 to the power of second plus 2 to the power of n plus 2 is divisible by 5. Let's correct this and try again. This is a real-world scenario you'll often face in your studies. Okay, let's correct that last example. I'm going to update the problem. We want to prove that 3 to the 2n minus 1 is divisible by 8 for all integers, and greater than or equal to 1. This one works out beautifully. Base case, for n equals 1. P of 1 is 3 squared minus 1, which is 9 minus 1, or 8. And 8 is divisible by sin. Base case is true. Inductive hypothesis. Assume P of k is true. That is, assume that for some integer k, 3 to the 2k minus 1 is divisible by 8. This means 3 to the 2k minus 1 equals 8 minium for some integer m. Goal. Prove P of k plus 1 is true. That is, prove that 3 to the 2k plus 1 minus 1 is divisible by 8. Let's work with the expression for P of k plus 1. We expand it as 3 to the 2k times 3 squared minus 1. This is 9 times 3 to the 2k minus 1. Now, our inductive hypothesis states that 3 to the 2k minus 1 equals 8 m. We can rearrange this to get 3 to the 2k equals 8 mem plus 1. Since m is an integer, 9m plus 1 is also an integer. This shows that the expression is 8 times an integer, which means it is divisible by 8. We have successfully shown that if p to k is true, then p k to 1 is also true. Therefore, by the principle of mathematical induction, the statement holds for all integers and greater than or equal to 1. Let's recap what we've accomplished. Today, our main goal was to start building your mathematical maturity. We tackled the precise definition of a limit using the epsilon-delta framework, working through several examples to understand how to construct these proofs. We then extended this idea to proving the convergence of sequences, learning the key technique of bounding to handle more complex terms. And finally, we explored the powerful tool of mathematical induction to prove properties that hold for all integers, seeing how the base case and inductive step work together. You now have a solid foundation in these essential proof techniques. Mathematical maturity isn't something you gain in a single video. It's a skill you develop through practice. The best way to build it is to try these things for yourself. So, here are some practice questions for you to work through. Pause the video and give them a shot. The solutions will follow. Epsilon-delta practice. Prove the limit as x approaches 3 of 4x minus 1 is 11, and prove the limit as x approaches 0 of x cubed plus 5x is 0. Convergence practice. Prove that the sequence a sub n equals n plus 1 over 2n minus 1 converges to 1/2, and prove that a sub n equals n divided by n squared plus 1 converges to 0. Induction practice. Prove that 1 times 2 plus 2 times 3, all the way up to n times n plus 1, equals n times n plus 1 times n plus 2, divided by 3. Take your time. Remember the process. Start with the conclusion and work backward. For induction, remember the 2 steps. When you're ready, unpause for the solutions. Welcome back. Let's look at the solutions to those practice problems. For the first epsilon-delta proof, you should have found that delta can be chosen as epsilon over 4. For the second, delta can be the minimum of 1 and epsilon over 6. For the sequence convergence problems, the first requires bounding, and you can choose n to be the ceiling of epsilon over 2. The second is simpler. You can choose n to be the ceiling of 2 over epsilon. And for the induction proof, after your base case and hypothesis, the inductive step involves substituting n times n plus 1 times n plus 2 over 3 into the left side of the pn plus 1 equation and simplifying to get the right side. How did you do? If you found these challenging, that's completely normal. The real learning happens when you struggle and figure things out. If you got them right, fantastic work. Keep challenging yourself with more problems. Thank you for joining me today. I hope this guide has helped you take a significant step in your journey to mathematical maturity. See you next time. Wait, I just noticed a mistake in my solution for the first convergence problem. This is another excellent opportunity to learn from our mistakes, just like in our divisibility example. Let's re-examine the target inequality for slota n plus 1 over 2n1, converging to 1/2. After finding a common denominator, we get the absolute value of 3 divided by 2 times the quantity n minus 1. Since n is a natural number, 4n minus 2 is positive. So we have 3 over 4n minus 2 is less than epsilon. Now we solve for n. We find that n must be greater than 3/4 plus 1/2. Therefore, the correct n to choose is the ceiling of 3 over 4 epsilon plus 1/2. My apologies for the error, but I hope seeing the correction process is a valuable part of building your mathematical maturity. It's a reminder that even mathematicians make mistakes, and finding and correcting them is a crucial part of the learning process.